Hey everybody, my name is Matt Snyder. I'm a PhD student here at North Carolina State University. I'm also a member of the Namibia Wildlife Aerial Observatory, which is a study abroad research program based out of NC State's Mechanical and Aerospace Engineering Department. The function of the Wildlife Aerial Observatory is to try to bring engineers and ecologists into closer partnership and proximity to try to solve some of these conservation conundrums. So the goal is to develop wildlife monitoring methods for African-led, African-skilled, internationally partnered research organization or conservation organizations. So the challenge that we're tackling is based around the current aerial monitoring system for wildlife. The current standard is to use single-engine aircraft, things like Cessnas, in order to monitor wildlife from the air. Now, the current team framework for this is to have one pilot, two observers, and one recorder who are flying around the landscape in these transect patterns on these east-west transects in order to count wildlife from the air. Now, this is a very useful tactic in Africa because many of the conservation landscapes there are these arid savannas or these dry scrublands, vegetation types that make it a little bit easier to spot large mammals from the air. So we want to be able to see if we can replace manned aircraft with drones, and there's a couple of reasons for this. One of these reasons is safety. Unfortunately, single-engine aircraft crashes have proven to be the highest cause of death for conservationists who are working across the world, and this is especially true in Africa, where aircraft maintenance can be difficult to receive. There's few skilled mechanics and very few parts replacements, and some of these airstrips that these aircraft are operating out of can be rough on airframes. The second reason is cost. Simply put, these manned aerial flights can be many thousands of dollars in order to conduct a landscape-wide monitoring survey. And as a result of that, many of these conservation organizations can only afford to do wildlife monitoring surveys once every 3, maybe 5 years or so. In contrast to that, drone technology is rapidly accelerating to the point that the cost points are coming down in a fashion where you might be able to support drone flights for wildlife monitoring at a quarterly level or possibly a monthly level. And infrastructure-wise, many of these drones are being flown with battery power, like ours, which means that you remove the costs of some of the fuel costs for many of these flights, which can end up being pretty profound. The third reason is accuracy. Recent studies have shown that sometimes there's discrepancies in terms of aerial observations from fast-moving, low-flying manned aircraft because you're relying on the observers to count or detect a group to be able to accurately count that group size and send that information to the recorder, communicate that information to the recorder in an accurate level. Versus with drone flights, since all of it is being recorded with our sensor mounts, our cameras, we can go back through the data and parse it very carefully in order to be able to accurately count all of the animals. So we chose to work in Namibia, and one of the reasons for this is that a relatively large percentage of Namibia is under conservation easements. Some of them are state-managed conservation areas, some of them are communally managed, and many of them are also privately managed conservation areas. But a large percentage of Namibia is protected, and a lot of this has to do with the really strong sense of pride for natural history that Namibia has, and it's well-founded. It has a very unique set of habitats, and many of these habitat types, like these arid savannas, dry bushcapes, are ripe for using aerial survey methods. The organization we partnered with directly is Nkuse Foundation, and we were flying out of their Nkuse Wildlife Sanctuary, which is a relatively large property just to the east of Windhoek. You can see some of our transects mapped out against the entire property right here. So Runkusei proved to be a very good partner for the Wildlife Aerial Observatory, and they were good at communicating their management goals. They wanted to look at some of these population trends. They wanted to see it especially in light of drought pressures and looking at it from a poaching perspective so that they could make the most informed decisions based on the mammal populations that were under their care. So in order to look at how adoptable our new methods might be for African-led, African-skilled, internationally partnered research organizations, we brought in a framework to help us see which parts might be the bottleneck for adopting this kind of technique. The first thing we looked at was hardware. Now there's a lot of drones that are coming off the shelf for a little bit more of a hobbyist approach. Many of these quadcopter drones are very, very capable for recreational use and things like that, and they end up having a lower price point as time goes on, as well as a spin-up in capability. Now, we tried to modify these hobbyist drone systems, a lot of these quadcopters, to try to give us the range that we needed, to try to give us better command and control communications and things like that. And as much as we were updating and modifying these quadcopters, we just simply could not get them to the range or the speed or the distance away from the base station to be able to use these as a replacement for manned aircraft flight, those single-engine fixed-wing manned aircraft. So what we did is we adopt a fixed-wing model ourselves. This is a 2-engine Believer, and this is what was able to get us out to ranges that we could start to compete with some of these manned aerial flights. We're flying these drones for well over an hour. You can fly them at 60, 80 kilometers an hour to be able to cover a lot of landscape, and they're able to operate semi-autonomously in order to follow our research routes. And this was a very interesting learning experience for me because I'd never looked at drone provision or drone design from the ground up. So there was a lot of really cool, interesting research heights, but I came to understand some of the sadness that comes with cutting edge technology, for sure. So I'm going to be honest, like from an ecologist point of view, I still needed engineering support for these drone adopted platforms. I'm a wildlife ecologist. I study movement ecology and population dynamics and patterns within community species richness and things like that. I don't have the technical skills to build a drone. So this is a point that we still need to kind of hammer out the details, sand off the sharp edges in order to get them to a point that they can be adopted by African research organizations at the moment. Now, from a study design point of view, I wanted to look at, we already covered some of the parts about trying to outperform airplanes for value, but I also wanted to look at this in terms of, can we have drones replacing some of the ground counts that we have for larger mammals? So as we went over, we have the aerial flights here, but there are many ground-conducted surveys because they end up being a little bit cheaper that I was trying to see if we could develop techniques for either verifying, like ground truthing the data coming out of ground counts, or to replace some of those ground counts with drones to try to bring down team size or bring down the amount of human hours required to do these surveys. So these counts require relatively small teams. Like the drone team can be as small as 2 people potentially. Most of the time we had 4, just so that we could have coders working on some of the transect paths. We had the pilots and then people who are monitoring some of the maintenance configurations. And we paired that against highly professional, very proficient ground teams who are going in and doing ground surveys. Now, the way that we conducted this is we would have the drones flying these transects looking down on these spaces that we were going to run our ground teams under. So these red points, this is an example from August in Namibia, and the red points are points where the drone was observing groups of animals, and then we walked a walking team right under these aerial surveys at the same time. So then we were looking at where the ground teams were recording animals and of what group size and which species compositions, so that we could directly compare where the drones were observing animals and where the humans were observing animals in a traditional ground count technique. And we'll go over the results of that in a second. So from a study design point of view, the drones were able to replace planes from a one-to-one perspective in terms of being able to cover the landscape. But now we rolled into a little bit of the data processing. So for us, data processing was a little bit different from the aerial systems because or a little bit different from the manned systems, because manned systems record all of the data in situ while they're in the plane, versus we had very high resolution data that we brought back to our labs, and we were able to pore over these images in very high detail, zoom in, change some of the inflection and framework and things like that in order to be able to verify to a little bit higher level that we were counting all of the animals. So here is an example of what we would be seeing from our aerial imagery. As you know, ecologists, I'm sure you can spot all of the animals in here, but just to help speed that along, this is a group of springbok moving through a semi-arid landscape in their kind of like herd movement formation. And if you zoom in, you can count each of these individuals in this particular herd. Now, it can be a little bit difficult to spot these guys from the air, and that kind of showed us that we understand why some of these manned aerial counts with 2 observers might miss some of these, because even things as large as elephants can be difficult to detect from the air. Elephants have a pattern that makes them a little bit similar to some of these bushy trees, and unless you know exactly what you're looking for, some of these animals, even the size of the largest land mammal in the world, can be difficult to observe from the air, which is why I was glad that we had all of our imagery to pore over and go through in a little bit more detail on the ground with pairs of eyes. One of the things that helped us speed this counting mechanism along was one of our engineers was a little bit annoyed that we made him open up every individual picture and zoom in, zoom out on stuff. So he actually wrote a program for us after dinner in order to speed along the tabulation and the recording of how all of our animals were seen. So he built drop-down menus, and he made it all very easily exportable on through Microsoft Excel, so that we could tabulate animals that were counted, animals that were seen in previous images, what group sizes were, and where they were seen on the transect. So from a data processing perspective, I'd say the biggest bottleneck was the fact that it took 10 hours to go through all of the data from a single morning's worth of transects, which means that it took us 150 total hours to process all of this data. Now remember those numbers, because we're going to come back to them. From a statistics point of view, we were able to look at some of these trends over time, build up a little bit of these detectability measures, and I'll go over some of those results right upcoming. But I do have to stress that this technique is not yet fully adoptable. We did have some challenges in terms of aircraft failures, which I'm glad that we did not have anybody in our aircraft, so our failures were always mechanical and repairable. Well, mostly repairable. Some days they were not repairable. And we were also able to provide a little bit more safety, not just for our animals, but also for some of the other residents. That being said, not all the residents were the happiest with our work. This is Clarence, and whenever we would fly over Clarence quite a bit at 6:30, 7 in the morning, and I think he took umbrage to this a little bit, because on the only chance that he was able to get to our drone, he surely showed us what he thought about that. So bringing up some of my study's results. So as you can see here, there's a little bit of a discrepancy in terms of drone and ground counts that we saw, which I found relatively interesting, because we were using ground counts that are similar to the standard that a lot of organizations use in terms of monitoring their wildlife. And we found that The drone surveys, with their paired ground surveys, the drones were seeing higher numbers of animals than the ground teams were seeing on the majority of flights, on the majority of paired comparisons. And this was true for individuals detected across all those transects. When we plotted that out, we saw that there's a pretty strong trend in favor of drones being able to observe these individuals on the landscape relative to ground points. And this was true for across most species. Now, there was a couple like plain zebras that appeared to be easier to detect from the ground, but by and large, most species were easier to observe from the air. And from this aerial data, we were able to actually build out some relative abundance hotspots maps in terms of our comparison and species richness hotspots. So our drones were able to produce this data to be able to see which areas in particular we were seeing both larger group sizes of animal and more different species of animals. Now, I shouldn't forget to mention that there were a few incidental bonuses in terms of management conservation, kind of the realities of conservation. There are a number of species like elephants and like rhinos that are very high risk of poaching due to certain syndicated poaching activities, unfortunately. And one interesting ride-along that we got from the conservation managers is through their intelligence gathering, through informants and stuff like that, it appeared that when you bring a bunch of Americans around flying drones, it appears to have a little bit of a suppressive effect on some of the interest in poaching in the landscapes that we were operating in, which I found interesting. So just a couple of things to tie in at the end. That point of adoptability that showed a little bit of difficulty, the data processing side of things, we found that there's rapidly accelerating tools that might help us alleviate some of these. From a people hour perspective, spending 10 hours to process one transect was a little bit difficult, but we've been able to develop here, one of the master students at NC State was able to develop a single shot detector that allowed us to rapidly increase the efficiency of our data count. So it went from 150 people hours to process to, once we had that data training set, now it took 10 hours to train the data and 1 hour to compute, to observe an entire season's worth of data collection, which drastically reduces the cost of being able to do these surveys. Once you've trained your algorithm, it can take an hour to go through an entire dry season or wet season's data very, very rapidly and be able to deliver you results without you having to invest a ton of very valuable people hours. Now, one of the most exciting things for me is that there's a ton of enthusiasm for this kind of work across Africa. Namibia University of Science and Technology students in particular, because they have an engineering school that we have partnered with in the past, there is a ton of interest in terms of adopting some of these technologies, being able to be that cutting edge, being able to be experts in the field and be able to kind of allow for much wider spread adoption for this. And we already see this in some other landscapes. This is the Grevy's Zebra Trust in northern Kenya, another organization that I have worked with a little bit, and they are very interested in seeing how the Grevy zebra habitat, or how the Grevy zebra populations are doing in light of things like increasing drought risk and changes in vegetative protective measures. So there's a lot of interest in this technology. There's a ton of really cool results that we can continue to get from this, and I'm hoping to publish some of those results in the near future so that more African-led, African-skilled, internationally partnered research organizations can really start using this on the ground. Thank you.